Apologies about not taking a while to separate videos. Uh, this stopwatch stuff is just to for debugging purposes, so I can see how long the path took. These are the waypoints, vector 3. Vector 3 just essentially means a point plotted in 3D space as it is in Unity, and this is the success variable on whether the path has been found. These create the two node objects for the start position and end position. There's just a tiny optimization as if neither of these points are walkable, the path isn't going to be found. These are the two data structures that I decided to use for the open set and closed set. The grid max size is, I think there was a method showing that before, you just get that from calculating grid x and grid y. I opted for a heap because quite a lot of heavy lifting is needed, and it's a lot more optimized as opposed to a hash set or list. And a hash set does just fine for the closed set, as not much work is done on it. So we start by adding the start node to the open set, and while the hash set, the heap, sorry, is not empty, remove the start node from the open set and add it into the closed set. This code here is previously when I used a list for the open set, and it's just using really a brute force for loop to iterate through everything, and it was pretty slow. So I opted for a hash set. This just means the path's been found, pretty much. So it stops the start watch, prints out a debug message, sets path success equal to true. However, it doesn't. There's still more stuff to do. So I haven't done a return here, just a break to get out of this while loop. So this goes through the neighbors, returns the neighbors thing from the method that you saw before. So it's saying that if the neighbor is not walkable or it's already in the closed set, we continue. So this calculates the new movement distance to the neighboring nodes, which is essentially the g cost plus the distance. The get distance method is actually down here. There's a pretty simple way of working it out. It's just essentially you plot how far away x is and how far away y is, and if x is greater, you do this little equation here, and if y is greater, you do this little equation here. So yeah, this calculates the new g cost essentially. So we check if the new path to the neighbor is shorter than the old path, or if the neighbor's not in the open list, which we're doing here. So we set the f cost to the neighbor, which we did up here. So g cost is that. Set the new h cost, again, just get distance, quite easy. And we set the parent of the neighbor to the current node, like this. And if the neighbor is not in the open set, we add it. Otherwise, we update it. And those are all heap methods, which are in the heap class. And if all of this you need to do this, it'll wait a frame because it's a coroutine, and it's got to be path success if we get down here. And this waypoints array, I'll show you how it works a little bit further down. And this is in the pathfinding class, which I'll explain in a little bit. Yeah, so once the path is found, just to make sure that it is actually right, we reverse the path. So create new lists, set the nodes to the end node, and this just kind of, in a way, like a linked list, iterates back through. So it adds the current node to the path and then sets the current node to what the previous node was, i.e. its parents. So this is just below. So this to simplify the path. Obviously, because it's tracing it from the end point back to the start point, we want to reverse it, so it goes from the start point to the end point, and this just returns the waypoints, which is used here to get the path. Yeah, so essentially, you're going to have loads of waypoints placed the way that we're currently doing it. So to simplify it somewhat, it's only going to place it at where the path changes direction, so that there's less work for it to do. And when it returns the waypoints array, we use it to simplify the path. So there's a lot less work to do up here. and this just starts the coroutine with the find path. Again, this is used a little bit more in the actual pathfinding script. This is just really very, very similar to how the tank stuff was used before in the fuzzy logic thing. There's a cute just to place place the new paths in every time the enemy moves. Again, this is the current path that will be the current path that the enemy is following. This just grabs the pathfinding class, and this says, are we currently processing a path? Just so we can access it, access the static method here that we've made. And this just sets the instance to an instance of this class and pathfinding. This grabs the pathfinding class. So this takes in path start and path end, called from the unit class, but sometimes we might not immediately get a response, so we need to maybe store in a method or something like that. So when a path is received, it can call the method and store it, and once the path has been calculated, it'll be stored in an action, it's just kind of like a callback function, very similar to a callback function. And this will be the actual path, and is the path a success or not. Creates a new path request, very simple. This is just the syntax to add to a queue, and is there another path? Do we need to call another path? And the try process next methods. Yeah. So if the path is being processed and the path queue isn't empty, this is just current path is sets the first thing in the queue to current path, and also takes it out the queue and says that its processing path is equal to true, and this just starts the coroutine with the path start and path end. This is called once the path is finished processing. So we call the current path using the action that was stored there, and whether it's a success or not. It says that it stopped processing a path, and if there is another path left to process, we call that method. And this is just a struct to store all the information from the path request class here. Is there anything? Yeah, this is just how you get a position in Unity. The transform, how fast it's going, the array for the path, the target, and the enemy tank. Again, this just requests the path from its position, its target's position, and the path found. Path request manager. Same thing. This is just a start method that's called once the game starts, and this just updates every frame. So again, if the path is successful, set path for the new path. If the enemy tank is dead, quit the game. Else. So I had a bit of trouble when I did start coroutine at the start and stop coroutine at the end. Never quite did figure out why, but changing them around seemed to make it work. So again, it's made it an I enumerator because it needs to stop and start depending on if there's a new path found. This is the distance between the enemy player. This is just saying, I was having index out of bounds errors when it actually found it, so this was a way of just making it stop 10 vector 3s away, and that stopped the error. Yeah, so the current waypoint by default is just the third position in the path array, but essentially while it's equal to true, if the transform position is equal to the current waypoint position, go to the next one, essentially. So yeah, target index ++, and if it's greater than the path length, just exit the coroutine, and it will set the current waypoint to the target index, and that essentially means that it is now ready to move towards the current player. Oh yeah, and the heap. Right, so a binary heap is a lot quicker to actually do the work for the closed set, and there are kind of two things that we've done here. So the first problem that we encounter is that you need to be able to add items, compare items, and so forth, right? So way to do that with a small interface allows you to keep track of its own index within the heap. It means you can compare two items and allow it to see which one is the highest priority in order to sort it in the heap. So allocate heap index as current item count, fairly straightforward. At the end of the heap array, not necessarily where it belongs, but it does. And again, you only sort up when you're adding to a heap. You never sort down, and at the end you just increment the current item counts. So the standard way of allocating a parent index in a binary heap is, the heap index minus 1 divided by 2. So this just essentially keeps sorting up until the item is less, because the compare to method returns 1, 0, or -1. It is lower, so it's going to, well, it's just, I probably could have done that in the actual method, to be fair. But this is just a standard, very standard swap method. Otherwise, if it's greater than 1, or if it's greater than 0, or it's 0, it's going to do this, or it's going to break, and then it finally makes the parent index the same as you do for extraction from a binary heap. Okay, it's a very standard boilerplate code of removing the first thing from a heap. Again, just contains update item. Yeah, so sort down method, only used once, but still fairly useful. Right, so it gets the indices of the two children because they need to be integers. It checks if the item has at least one child on the left, and changes the swap index to the left child. And then it also checks, can it have two children? Is there a child on the right? And again, swap it. And it checks if the parent has actually a lower priority than its highest priority child, and it swaps them. So if the parent is higher priority than the children, return. If the parent doesn't have any children, again, return. I think that's it. So just a few things to add. I haven't really adhered to object-oriented coding standards, which is something I'd like to have done in my evaluation. Inheritance is kind of done via, if you see here, maybe might be better to go to the fuzzy neural thing. Yeah, inheritance is done via this way. So got like a player tank or something like that, and let's say I wanted to access stuff here. I've actually put you can drag the player tank script into it like this, and it allows you access to all of the variables in that. The same way here, you'll probably see normally in Java or something like that, I would have just instantiated 4 neural controller objects and then assigned them to each of the objects that I created there. Not really possible, so that is how I did that. Right, I think that's it. Apologies for the length of the video, but thanks very much for watching.